Welcome to this video presentation on Output 2.1 Studies of Potential Solar Projects, which emerged from a SOLARISE project. My name is Victor Becerra and I am a professor at the School of Energy and Electronic Engineering at the University of Portsmouth in the UK. Here are the contents of my talk. First of all, I will provide an overview of SOLARISE. Then I will discuss feasibility studies of solar projects, starting from an introduction to feasibility studies in general, then discussing the main aspects of feasibility analysis in solar energy projects, and then discussing a methodology for decision making that we have developed in this project. I will then provide a list of feasibility studies that have been performed as part of SOLARISE, and I will provide a number of examples of SOLARISE installations of solar energy projects that have emerged starting from the feasibility studies that were initially carried out. And finally, I will provide pointers for further information. SOLARISE, which stands for Solar Adoption Rise in the 2Cs, is a research and innovation project that is funded by Interreg 2Cs and the European Regional Development Fund. The total project budget is in the region of 4 million euros. The consortium is made of 12 partners in 4 different countries: England, France, Belgium and the Netherlands. There are also 14 observer partners. SOLARISE is led by the University of Picardy, Jules Verne, in Amiens, France. There are 3 universities, 1 energy retailer, 7 local councils, and 1 smart energy organization. The objectives of the project are discussed here. The main objective of SOLARISE is to stimulate, broaden and accelerate solar adoption through the 2Cs region of Northern Europe by, first of all, identifying and overcoming barriers to solar adoption. Also using smart grids, electricity and heat storage, Internet of Things and energy management systems to facilitate the adoption. Also by proposing cost-effective and affordable solutions that enable end users to adopt solar energy. Moreover, we will do this by implementing innovative living labs and a series of demonstrations in public buildings, infrastructure and in households with low-income families. And finally, we are doing this by delivering training tools and roadmaps. I'm going to introduce now the concept of feasibility studies. Feasibility studies are a set of investigation that establishes whether a project or plan meets the conditions to be implemented, to be made reality. And then the feasibility study makes recommendations on whether or not the plans should go ahead, and also under what circumstances the project should be going ahead. Okay? It may also help to select any options that may have been considered during the initial planning stage. The objectives of the feasibility studies include typically to give focus to the project, to provide valuable information for a go or no-go decision to be made, to narrow the different alternatives that are considered, to also increase the chances of success by identifying any weaknesses at a very early stage, even before money or resources are invested, and also by enhancing the success rate by evaluating these different alternatives and choosing objectively the best ones. Finally, considering the life cycle and the impact of the project. Now, why are feasibility studies important? They offer the opportunity to get it right before committing time, money, and business resources. They also help to avoid additional costs to correct any flaws and remove limitations that could have been identified earlier. They may also help identify new possibilities, opportunities, and solutions. The main aspects that are analyzed when looking at the feasibility of solar energy projects are listed here. There are technical aspects also associated with the site or the location of the project. There are financial aspects, environmental aspects, and also social and legal aspects. All of these need to be considered together so that decisions or recommendations in relation to feasibility can be made. Let's discuss technical aspects. First, it is very important to predict the electricity production capacity of the solar plant. For this, of course, engineering studies need to be carried out. The optimal location and orientation of the solar array and the optimal panel tilt need to be estimated. Surveys for open terrain or roof-based and building roof-integrated systems need to be carried out, and decisions made on the basis of the outcomes of those surveys. Solar panel mounting options need to be considered. There may be different possibilities here. Roof measurements and roof condition assessments need to be carried out. It is important as well to consider the local shading that may occur because of the presence of nearby structures. It is also important to assess the need for any electrical, roof, ground, or any other kinds of works, so that their cost and implications can be considered as part of the analysis. It is necessary to assess any potential on-site hazards and risks. It is very important to identify any site access restrictions and to identify any potential grid connection restrictions in the area. In terms of financial aspects, it is important to say that financing a commercial solar project is possible when the plant is highly likely to generate sufficient revenue to pay for any debt, taxes, costs, and then produce an acceptable return for the equity that is invested. The decision to proceed with the development of a commercial solar energy project depends heavily on the financial viability of the project. Therefore, this financial viability is analyzed very carefully. The annual energy yield directly drives the revenue line in the cash flow model. Accurate energy yield predictions are very important in large-scale projects. There is also uncertainty in relation to the yield predictions, and this uncertainty needs to be estimated as well. The key revenue stream for most solar plants is the tariff that is paid for each kilowatt hour of electricity that is generated, assuming that we're talking about a photovoltaic solar plant. Power purchase agreements can be signed with a commercial buyer, for example. Sometimes there are other sources of revenue, such as renewable energy credits, tax credits, and so on. The permanency of any of these incentives should be assessed carefully, as they are often modified or even eliminated by the government with little notice. Tariffs and incentives do vary from country to country. There are key indicators that are used very often to assess the financial viability of a solar energy project. These indicators include for example, the net present value, the internal rate of return, the payback period, the cash flow available for debt service, the debt service coverage ratio, the loan life coverage ratio, and the levelized cost of electricity. Depending on the project, different metrics are used, but typically at least the payback period and the net present value are calculated. In terms of environmental aspects, it is important that the potential environmental impacts associated with a solar energy project are analyzed carefully. These impacts may include the land use and habitat loss, water use, the impacts associated with manufacturing, for example, the use of certain chemicals during manufacturing, any landscape and visual impacts, as well as global warming emissions associated with the plant. These can vary widely depending on the technology that is used, the location, the scale, and other aspects of the project. When a habitat is destroyed, the local organisms decline or disappear. Larger utility-scale facilities can bring about worries about land degradation and habitat loss because of their size. The total land area requirement depends on the technology that is used, the topography, and the intensity of the solar resource of the location. Habitat loss impacts from utility-scale systems can be mitigated by locating them at lower quality land, such as former landfills, for example. There is also the aspect of ground concurrency. It is not desirable to displace potentially productive agricultural land as a result of a solar installation. A possibility that is being considered these days is to design a low-impact solar development, including the co-location of solar and agriculture. This has the potential to alleviate agricultural displacement by allowing solar arrays, vegetation, and livestock to occupy the same land area. There is also the issue of water use. Solar photovoltaic cells don't use water for generating electricity. Some water may be used from time to time to wash the panels if necessary. And there is also water usage associated with the manufacturing of the PV components. Concentrating solar thermal plants, this is another type of solar plant, use water for cooling and washing. And this is significantly more than in the case of photovoltaic plants. Water use depends on the plant design, the location, and the type of cooling system. It is also important to analyze the environmental impact of solar energy systems in relation to the life cycle, of these systems. Solar energy systems provide significant environmental benefits in comparison to conventional energy sources, such as using fossil fuels to generate electricity. Sometimes, however, the wide-scale deployment may have potential negative environmental implications. And perhaps the simplest measure is to consider the global warming emissions that are associated to the solar installation. And this may consider the whole cycle from manufacturing of components to disposal and recycling of materials. Another aspect which is important to consider is that of landscape and visual impacts. They can include, for example, the visibility of the solar panels within the wider landscape and the surrounding communities. Possible mitigation measures include the consideration of the layout, the size, and the scale during the design process. Also landscaping and planting to screen the modules. Glint and glare should also be considered in the environmental assessment process. Of course, as mentioned, one of the key benefits of solar energy technology is the reduction in carbon emissions because of the substitution of fossil fuel generation that a solar installation enables, which has a positive impact in the environment. A simple initial calculation of this reduction assumes that all solar electricity directly replaces electricity that is produced by large power stations. A common method uses the average grid carbon intensity, which is the average amount of CO2 that is emitted for each kilowatt hour of electricity that is produced for the power grid. This, of course, depends on the country or the region, and in the case of the UK, this quantity is estimated at present at around 233 grams of CO2 per kilowatt hour of electricity produced. Then there are legal and social aspects that need to be considered at the feasibility stage. In terms of legal aspects, we have that permits and licensing can be a lengthy process that may involve multiple agencies in the central and local governments. Depending on the characteristics of the project, some of the following may be needed: land lease agreement, site access permit, planning permission, an environmental permit, grid connection agreement from the distribution network operator, as well as operator generation license. All these take time, and some of them may be more difficult depending on the characteristics of the project and the location. There may also be impacts on cultural heritage. These impacts can include effects on the setting of designated heritage sites or even direct impacts on underground archaeological deposits. It may be necessary to carry out field surveys prior to any construction, and these surveys may be part of the feasibility study. Mitigation measures can include careful site layout and design to avoid areas of cultural heritage or archaeological value. Alternatively, it may be possible to use modern photovoltaic technologies in order to design installations that are extremely discreet and not very visible. For example, through the use of solar tiles. Proposing solar installations on a listed or protected building will always require planning permission, and this process needs to be managed extremely carefully. As part of this project, we developed a methodology to assess feasibility. Solar feasibility studies consider a range of technical, financial, environmental, as well as legal and social aspects, as we have been discussing. We developed in this project a multi-criteria decision support system for solar feasibility studies based on rules and a scoring system. This enables users to compare different project alternatives and helps them make decisions that consider the relative importance of different criteria. This relative importance may change from project to project and from organization to organization. The methodology has been implemented in software using Excel, and it has been used by project partners to support their decision making. A case study based on a real-life solar farm has been published. In the published study, the method was used to identify an optimal configuration for the solar farm out of 9 alternatives. The work was published in the journal Energies in 2021. A number of feasibility studies were carried out in SOLARISE. They are listed on this slide. First one listed here is a sustainable renovation of a historic public building in Zoersel in Belgium. There was also the deployment of solar technologies at a heritage mill in Middelkerke in Belgium. There is the study of innovations for solar energy applications in historical and public buildings in Middelburg in the Netherlands, with the specific applications for 3 buildings. There was a study on the deployment of photovoltaic solar power generation systems at public buildings in Fourmi in France. There was a study on the development of solar technologies at social housing sites at Brighton and Hove City Council in the UK. There was also a solar farm feasibility study by Brighton and Hove City Council in the UK. There was a feasibility study emphasizing the environmental impact of a solar farm by Enercoop, a French energy retailer. There was a feasibility study for a solar farm by Herhoevoort in the Netherlands. There was a feasibility study for a concentrating solar plant by Flux 50 in Belgium. And there were feasibility studies for living labs at the universities of Portsmouth, University of Picardy, Jules Verne, and KU Leuven in Belgium. I will now present to you a number of solar installations that have been carried out by SOLARISE partners following initial feasibility studies that were carried out. First one is the Brighton and Hove social housing flats at Buckley Close in Brighton. Buckley Close is a new development that consists of 12 social housing flats within 3 blocks. Solar-generated electricity is to be consumed by tenants before it is exported to the grid. The self-consumption that is achieved by putting tenant supplies behind the meter allows Brighton and Hove City Council to charge tenants a reduced rate for electricity. Another example is the public buildings in Fourmi, in particular the École Aragon. Another example is the case of the Fourmi public building École Aragon. Solar PV panels were installed on a school roof, which serves the purpose of creating awareness about solar energy for the students and their parents. The system has a capacity of 98 kilowatt peak, as well as an annual energy production of 92.3 megawatt hour. The energy use in this case is mainly for self-consumption, and there is also sales of electricity to the grid. Another example, in this case in the Netherlands, is the mill at Middelkerke. The municipality installed a solar PV system with a peak capacity of 8.68 kilowatts, and as well as a 6 kilowatt hour battery storage system on the site of this heritage mill that was built originally in 1871. The energy is used on site, and also it is employed for charging points for bikes and cars. And finally, another example of a solar feasibility study that eventually was implemented and constructed is the case of the Solar Living Lab at Portsmouth. Major installation work was completed on the 7th of May 2021. The installation consists of a fully monitored solar array with a peak capacity of 5 kilowatts, a 5 kilowatt inverter, as well as a 13.5 kilowatt hour Tesla Powerwall 2 battery. These were installed at the Eco House, which is an experimental house that can be seen in the top left picture. Moreover, a 40 kilowatt hour Tesla battery storage system was installed at the Future Technology Center building to work together with the existing 25 kilowatt peak PV array that you can see on the roof of the building. Okay. Now this installation is complemented by a range of equipment that has been purchased to support undergraduate and postgraduate student projects. Now I wish to briefly discuss about sources for further information. There is an output report called O2.1 Studies of Potential Solar Projects that is available on the website in PDF format. The report contains fact sheets on analyzing feasibility of solar projects in historical buildings, public buildings, solar housing, solar farms, and living labs. It also contains a number of best practices that have been identified in this project in relation to the analysis pertaining to site, technical, financial, environmental, social, and legal aspects, as well as decision making. Thank you for your attention.